Hi, welcome to a video podcast on standing waves. Here's a little picture of a standing wave. One of the first things you're going to need to know is what are the conditions under which a stationary wave will form. And for a stationary wave to form, we need two progressive waves travelling in opposite directions, one this direction, one this direction. They need to have the same frequency and the same amplitude, and they need to be able to interfere. And in some places we'll get constructive interference, and here we have an anti-node. That's where the two waves are reinforcing. And we also have nodes, which are where we get destructive interference and there's no wave activity. You can see that that is one wavelength. So the different distance between two adjacent nodes is half a wavelength, and the distance between two adjacent antinodes is half a wavelength as well. Unlike a progressive wave where all points of the medium move with the same amplitude, we've got this smooth variation in amplitude with great amplitude at the antinode and no amplitude at the node. We've also only got two phases. Everything between these two nodes moves in phase, and this antinode is moving out of phase with that antinode. However, once you go to the antinode beyond that, these two antinodes are back in phase. There are only two phases, and if you go across two nodes, everything's moving back in phase again. The most common way of creating a standing wave you're most likely to see is to have a vibration generator or an oscillator at one end sending the waves this direction. They then reflect on the wall at the other end and come back, and that is the reflection that creates the progressive wave travelling in the opposite direction. Should know that the lowest possible frequency standing wave is called the fundamental. Obviously, the distance between the two nodes is lambda over 2, so the whole length of the standing wave is now a lambda over 2. The next shortest wavelength possible is with just a single node in the middle and a node at either end. This is all for waves on a string. And so this will occur at frequency f. Because this has got half the wavelength, it must have, for the same wave speed, double the frequency. It will be at 2f, and this will be at 3f because it's only got a third of the wavelength of this one, and so the pattern continues. One of the things that I know students find difficult, and we should just think about for a moment, is if we're shown a snapshot of a standing wave and we're asked to redraw the standing wave as it would appear after a certain amount of time. So if we keep the numbers simple for the moment, let's imagine we're told that this standing wave occurs at a frequency of 10 Hertz. We know as ever that the time period is 1 over the frequency. So the time period is 0.10 seconds for this wave. So say we were asked to draw what the wave would look like after 0.025 seconds. Well, 0.025 goes 4 times into 0.1, so that's 1/4 of a cycle. So we look at this point on the wave here. I'm just going to change colour to make it a bit less confusing. This point on the wave here will have moved all the way to here and back again in one cycle. So in half a cycle it has moved to there, in 1/4 of a cycle it has moved to there. Similarly, in 1/4 of a cycle that will move to there, that will move to there. So after 0.025 seconds, then that's what the wave will look like. So what would it look like after 0.5 seconds? Well, that's half a cycle, so each point would have moved completely to the opposite side. So that's what the wave would look like after 0.05 seconds. So the key thing here is if you're asked to draw the standing wave after a certain amount of time, is to calculate the time period, find out what fraction of a time period the time you're given is, and then just count through what fraction of a cycle it's operated. If you find something less than a quarter, you might be asked, where would the wave be after an eighth of a cycle? You can draw anywhere realistically between maximum displacement. So this is not a bad picture of what the wave would look like after an eighth of a cycle. Okay, I think you've found that useful. Thank you.